All right. I always get a question from students about right-hand rules, and they pop up a lot. So I tried to draw today. I'm not that good at drawing on a tablet to begin with, but I did try to draw today for you guys a picture of a hand, a right hand in this position, right, where this index finger makes a 90-degree with the middle finger, and both of them make a 90-degree angle with the thumb, and that sort of thing. So I did try to draw that for you to give you some idea of the right hand rule, so you can at least picture this in your head. So let me start by sharing the screen. Okay, so this is a drawing I did of a hand. You can tell like the ring finger and the pinky finger are a little short, the palm's a little wide, but I just sort of quickly threw it together. The main thing I want you to see on this is the equations at the top that are really important. We're going to go over that in a second, but I know the big drawing at the bottom is probably the thing that's going to catch your eye, so I figured I better go over that first. So for starters, we know we can calculate a vector by using what we call the vector or cross product. Those are two words for the same thing: vector product, cross product. So vector product is equal to the cross product. Okay, we already studied a dot product, which is also called a scalar product. And in fact, you can see that in the equations above. But what I'm talking about right now is a vector product, i.e. a cross product. So if you take a cross product of A cross B, then you can figure out the direction of that answer, because the answer will be the direction that your thumb points. Notice that I drew a vector A pointing along the index finger, and I said this is A. I also said this is QV, and later on I wrote goofily that it's also, whoa, I did not expect that to happen. It's also L. Okay, so for instance, in that equation, IL cross B, it's also L, and let me go ahead and at least make it the consistent L. So I'll say it's like that. Okay, so in these three cross products that you see right here, here, and here, the first vector is either A, which you see here, or QV, which you see here, or L, which you see here, and you see all of those correspond to the index finger of the right hand. You also see that the second vector, B, or B, or B, yeah, literally they all turned out to be B, points along your middle finger. And then the answer, A cross B, or QV cross B, or IL cross B, points in the direction of your thumb. I could also add in there, by the way, what did we use? We used IDL cross B as well. So that's another one that could be there, in which case the A would have to be DL. So I could say down here, just to make it consistent, I could go ahead and write R DL. Okay, so that's a sort of a big moment for you guys to see finally what's the right hand rule. There's other versions, other ways of looking at the right hand rule. Hopefully this one alone is good enough to help you. Does anybody have any questions on that now? All right. So what I also hope to do is just refresh your memory. So far, if you look at the equations, I'm starting right under the URL for my YouTube channel. It says F is equal to QE. That's where that came from, the definition of electric field. So we know that the force on a charge Q subjected to an electric field, E, is given by QE. Similarly, we know that the force on a charge Q with a velocity V is given by QV cross B. And I even remind you that the cross product can be calculated by taking the determinant of that matrix that you see there, where the first row is I hat, J hat, K hat. The second row is the Cartesian coordinates of A. The third row is the Cartesian coordinates of B. And then you just do the determinant of that matrix, and that gives you the actual formula. You can look in the notes, which obviously I told you before that they're being posted every day on my Google Docs, so you can download those there anytime you want. And there is access to Google Docs that you can get up at the top of my Canvas page, so make sure you do that. I also reminded you that you can just blindly calculate the magnitude of A cross B by taking the magnitude of A, multiplying it by the magnitude of B, and multiplying that by the sine of the angle between them when they're tail to tail. So that's that equation right there. And I even drew a little diagram to help you understand what I'm talking about. I've already covered this one. I've already covered this one. I've already covered this one. Okay. I also want to remind you that we learned last semester, hopefully you learned last semester or previously in your 241 class, that the dot product, which is also called the scalar product, which equals the scalar product. So that means you take two vectors in and out pops a scalar, a regular number. So the dot product can be found by multiplying like components and then adding the answers up. So you take the X components of A and B and you multiply them. You take the X component or the Y components of A and B and you multiply them. You take the Z components of A and B and you multiply them. And then you add those. You add those three products together according to the sign rules that you have. So for instance, you know, some of the components would have had negatives and some of them would have two negatives. So you have to use your proper signs when you're multiplying AX times BX and AY times BY and AZ times BZ. But when you're finished with each of those products, you add those three together and that gives you the dot product. And another way that the dot product can be calculated is the magnitude of A times the magnitude of B times the cosine of the angle between them. Having two ways like that means that that dot product can be used quite nicely to figure out the angle between two vectors. That comes in handy in material science, solid state physics, stuff of that sort. We did find that, of course, just like we found that a force F is given by QV cross B when a charge Q has a velocity V is going through a magnetic field B. But we also found that if you have a length of wire L with a current going in the same direction as L, then IL cross B is the force that results from that. Or we can chop it up into little differential segments in case the wire is actually bending as opposed to being really straight. And in that case, you get this nice little equation. So, and I used that last time to show you, for instance, how to calculate the force on a semicircular loop of current carrying wire. That and the like day one Coulombs Law used to calculate the magnet or the electric field from an infinitely long wire. Those are sort of the holy grail of this course. Those are the tests that say, hey, I really got this. It's not to say that if you can't do it, you aren't going to pass or anything like that. It just means, hey, I really got this. So make sure you try to really hard to try to understand how to apply those integrals that we did in chapters 21, 22, and 23. And again, try to make sure you can understand those integrals I did yesterday and the ones I'll do today. We also found that there exists a electric dipole P. I've given you a little picture of it here. If you imagine a little vector whose length is lowercase d, and it points from a negative charge, negative Q, to another charge, positive Q, then the dipole moment, the electric dipole moment of that is just the charge Q times D. Okay, and that's always a positive quantity, by the way. You just use the positive Q, and then you make sure the D vector points from the negative charge towards the positive charge, and you'll have P, the electric dipole moment. It turns out when you put a electric dipole in an electric field, it experiences a torque given by torque equals P cross E. And when you put it in an electric field, it also experiences a potential energy given by negative P dot E. So there's a dot product being used there. Well, there also happens to be a magnetic dipole moment, and I made it so small it's not very easy to see, but what I'm trying to draw there is a circular loop of current carrying a current I. So you see the little arrows? They're suggesting the direction that the current is going. So the current is going, if we look from above, the current is going in a counterclockwise direction around that wire. But if you look, you can see one wire, two wires, three wires, and what you're supposed to see is dot, 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 like that. So in other words, we have ultimately N turns of wire. If that's the case, then the magnetic dipole moment is N, the number of turns, times I, the current, times A, the area, and we represent it by a vector, and that vector is given by a right-hand rule again. So I lay my right hand on the current carrying wire so that my fingers of my right hand curl in the same direction as the current goes, and then my right thumb points in the direction of the vector. So you can see that's consistent with this. Excuse me, with this picture. You can see, for instance, that if I laid my right hand fingers, my pinky would go obviously from the right side up and around the top and then down the left side, and my thumb would point straight up. What I did was imagine a little unit vector N hat that would be perpendicular to that plane that electric current is in. And then I said the area vector A would be pi times r squared because it's a circular one, but whatever shape the area is, it's just the area times a unit vector pointing perpendicular to it. And then you take that area, multiply it by N, multiply it by I, and then you got the magnetic dipole moment. So now that we have that, we can also see that there's a torque that comes from putting a magnetic dipole in a magnetic field. And just like in the electric case, it's given by mu cross B. Instead of P cross E, it's mu cross B. And again, it also gets a potential energy, but instead of negative P dot E, it gets negative mu dot B. Okay. So that's sort of the big stuff we've learned so far. Any questions on that? All right, so it turns out, and I've warned you about this before, I said, there's only one experiment we can do to determine whether in reality conventional current is real or not. In other words, we picture, if this were a wire, we picture conventional current as if the current's flowing this way, that means positive particles are flowing this direction. And I've told you that in reality, it's actually negative charges going the other way, but there's really only one type of experiment you can do to really discern which is true. And with that being the case, you need to know about that experiment. Okay, so I'm going to start off now with telling you about that experiment. That experiment is the Hall effect. Okay. And it can be used to help us figure out neat little things about nature, about the way matter behaves, all sorts of cool stuff like that. So that's part of the reason that I'm telling you about the Hall effect. And not only that, in understanding how the magnetic field and the electric field both act on current carrying wires or individual point particles, we actually have a lot of technology that can be used or that can use those facts. For instance, if you look in your textbook in section 27, or excuse me, in chapter 27 at figure 2719, you'll see a device which is more or less the same device that we use in our lab on magnetic deflections, only this one is in a controlled environment where it's a little safer. In other words, they had to put such a large magnetic field and such an energetic electron beam that you wouldn't want to use this setup for lab, but in doing so, they were able to get an actual electron to complete whole circles within the discharge tube, unlike what we did in class where we could just get a little bit of one. So figure 2719 is quite nice at showing that. I'll probably even pull that up later. But what I want to go for right now is the Hall effect. And with the Hall effect, basically what you do is you take a current carrying wire and you predict if current's going to the right, the positive particles are either going to the right or the negative particles are going to the left. Let's see if we can do something to mess around with that. And if we can, maybe we can use those results to make sense of them. So that's what I'm actually shooting for. Anybody have any questions on that as I move along? No questions. I saw somebody put something in the chat. Let me see. Can't use lockdown browser. Okay, we do have other options. So for instance, a student asked about a lockdown browser. If your computer will not use Respondus lockdown browser or Respondus monitor, then you're going to have to set up a testing facility. TCC does that for free. So you just need to let me know that you're going to use that and I'll set it up for you. And you can go to your nearest campus. You don't have to go to, for instance, my campus, which is Virginia Beach. You can actually just go to the Chesapeake campus or Portsmouth campus, whichever one you live closest to. So that's kind of nice. But yeah, that's what you have to do if you can't get your computer to run Respondus and the lockdown monitor and the Respondus, the monitor, not just the lockdown browser. All right. The other thing. Yes, somebody have a question?
Is that what we use for the test?
Yes, that's what you're going to use for the test. You'll be on Respondus lockdown browser. And not only that, I will put up a practice midterm that you do exactly once. Pay attention here, everybody. I know somebody's going to ask me this anyways. So you do it exactly once, but the main thing is you do it immediately to test whether your browser and your computer that you're using, so you want to use the actual computer you're planning on taking the test with, you want to see whether that runs Respondus lockdown browser and whether that runs Respondus monitor. So you have to use that computer, and I don't care if you've done it, in previous classes. It's very, very important. Everybody listen to me. It's very, very important. You have to do this, because if you don't do it, even if it's worked before for you, then what could happen is you go to take the test the day of the test, and your Respondus browser software will not be up to date, and you'll lose quite a bit of time in doing that, and might not even be able to finish your exam in the allotted time, might even have to reschedule the exam in the allotted time. And that means you're going to get an entirely different exam, and it's probably not going to be as nice as the exam that everybody else gets. So make sure y'all do that exactly once. There will be another practice midterm that you are supposed to take over and over and over again, and it doesn't require any Respondus lockdown browser or anything. That's the one you're taking. That's the one you're going to grade. That's going to go counting for your grade for extra credit. The other one, though, has to be taken once, and I'd say take it as soon as it comes up within a day or two, and maybe even check it again a day before you're actually planning on taking the midterm, just to make sure nothing else has been updated. Any questions on that? All right. So let me pull up my screen again so I can show you the dealio. Check out my use of foreign language. Pretty sure that's a foreign language, dealio. I'm making fun of myself here. Okay, so the thing we're talking about is called the Hall effect. And the Hall effect is what allows us to determine, as I said, whether or not we actually have positive charge carriers or negative charge carriers at current carrying wires. So here's what I'm going to do. I'm going to imagine a current carrying wire, and the current carrying wire is horizontal like this. Okay. So that's what I've got. I've got a current carrying wire that's horizontal, and that could be a result of, well, let's just put it this way. I will say definitively that the current is going this way. So that is our current direction, I. Now I have two scenarios by which this might be happening. The scenario is I've got a positive flow of particles going this direction, or I've got a negative flow of particles going that direction. Okay. Now, how do we deal with this? Well, it turns out that you can get a little asymmetry up in here by applying some knowledge about magnetic fields. So let's say the magnetic field is going to be indicated by the color green. And let's say I have a fairly uniform magnetic field that's actually acting into the board like this. And remember, when you see X's, that's like you're looking at the back of the arrow, like a bow and arrow, where the little feathers are that sticks off to the side. So that's what I'm trying to show you, that it's a magnetic field that is actually pointing into the page like this. Now, according, and you guys work this out now, I want you to first think about the velocity of the negative charge carriers. That's the little blue vector you see over there. And I want you to think of what exactly is the direction of QV. Remember, you can multiply a scalar Q times a vector V, and it does things to the vector. So everybody think about which direction QV is, and then use your new right-hand rule with QV and B to figure out which direction a negative charge would be deflected. Everybody should try to do that and make a prediction before I draw it. Then once you've done that, hopefully you've already completed it. Once you've done that, I want you to think about the positive charge and what happens to the velocity V when I multiply it by a positive charge. And then I want you to use your fancy right-hand rule that I have shown here again with my hand. What happens to it, and therefore which direction will positive particles be deflected? Now I'm going to draw the answers. So it turns out the positive charge, of course, is QV would be actually to the right. Let me do it this way. So QV would be to the right, like this. I'm going to use my index finger to point to, actually I said to the right for the positive charges. That's actually to my left. I don't know why I even said that. I'm looking at the part that you are. Yeah, I don't know what happened. Anyway, so QV is this way for me. right? Magnetic field points into the board. That means I got to turn my hand like this so that my middle finger is now pointing towards my computer screen. And I see that my thumb points down. So in fact, what's going to happen is a bunch of little positive charges are going to pile up along the bottom of this wire. Hopefully everybody else found similar results. Now we're going to do the negative one, okay? The negative charge means that QV, even though V points to the right, QV points to the left. So QV again is to the left. I push my index finger to the left. I turn my hand so that my middle finger, which is B, points towards my computer screen. And then again, my right thumb points down, which means if we do this and it's actually negative charge carriers, then in fact, what's going to happen is we're going to get a accumulation of negative charges along the bottom edge. So we'll get negative here, negative here, negative here, negative here, negative here. Now that's a pretty cut and dry experimental result. All we really have to do now is I'm going to take the multimeter that you guys have been working in class with. I'm going to take that multimeter and I'm going to set it right over here. Okay, and I'm going to draw it like I'm a moron. So everybody, make sure y'all get a picture of the moron. Okay, and now I'm going to draw another one. All right, so I'm finally using the autocorrect so I don't look like a moron. Okay. Now what I have on this thing is a dial, and I'm going to set it to voltage that looks like this, dot, 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 and then has a straight line over it. So that's DC voltage. I know I have a COM port right here. And I know I have a red V comma omega port right here. What I am going to do is I am going to now connect a big fat red wire to this side. And now I'm going to connect a big fat black wire to this side. Okay. Now, oops. I went into moron mode again. Sorry about that. Well, I'm still going to do a little bit of moron mode, evidently. All right. So if in fact the red charges are the one moving, then we will have an electric field that points in fact this way. Let me take it off of moron free and put it back on moron so that it'll work. Okay, so that's the electric field if positive charges. Okay, now if in fact it is negative charges, then we'll have an electric field that points this way. And that's if negative charges. Okay, does everybody see why that's the case? Does anybody have any problems understanding why those electric fields point that way, depending on what the result is?
Can you explain that just one more time?
Absolutely. I'm glad you asked. Okay. So I think you've gotten to the point where you understand that the negative charges would end up pulling along the bottom edge if it's in fact negative charges. Did you make it that far? Was that understandable for you, Maya?
Yes.
And anybody else not understand that part?
Which part?
That if it's negative charges, then negative charges are going to be deflected downward and pile up against the bottom edge of that wire.
Is that because the negative is connected to it?
It's actually because QV cross B forces the negative charges to divert from their straight path to the right and makes them go downward. They're not necessarily going to stay there, but they're going to pile up along there as they're going through the wire. Does that make sense?
Yeah.
Okay, so that's one part I got to make sure everybody understands. It looks like y'all got that pretty well, so that's a good thing. Now, if there's a bunch of negative charges over there, that's sort of the equivalent of having a bunch of positive charges on the opposite side. And I think now you can see, oh, wow, this is starting to look, in fact, like a capacitor. And a capacitor would have the electric field pointing from the positive charges to the negative charges, because electric fields always point in the direction that a positive charge wants to go. Does that make sense? Electric fields always point the direction that a positive charge would be compelled to move. If we've got a pile of negative charges along the bottom edge, even though they're moving to the right too, that's still going to compel positive charges to try to move that way because they like opposite charges. That means the electric field, due to the Hall effect, and actually we should subscript that, I should put an H on it, just so you'll know, that's the electric field due to the Hall effect. There's an entirely different electric field that's driving the currents. I guess you should all know that, of course. But yeah, there's a different electric field that's actually making the current go to the left. But what's established by the magnetic field is a Hall electric field that actually either points down or up. In fact, we discovered that the electric field points down experimentally. Does that help you, Maya, or do you need more?
I think I get it.
You get it. Anybody else? Like I said, feel free to ask, guys. If you don't understand, there's almost 100% certainty that someone else doesn't either. So the reason why I put the voltmeter here is I want you to understand that when you connect a voltmeter, and that's what this multimeter is when I've got it connected to V, when you connect it, it's expecting the red side to be a higher voltage than the black side. And in fact, since the experimental result says that the electric field will actually compel positive charges to go downward, then that means I will actually get a positive reading in here. And we could call that, for instance, the Hall electric potential. Okay. Now, what's going to happen is just like we had with when we first started studying current, we discovered that there was a drift velocity that occurred, and that drift velocity was related to J and all that good stuff. In fact, what we found is that J, which was a vector, is equal to, in magnitude at least, I over A. So let me, since I've started off with a vector, all gung-ho and stuff, let me say J, the vector magnitude, is the current divided by the cross-sectional area of the wire, okay? Now, in vector form, that means J, we found, was in fact equal to negative the charge of the electron, because we know it's actual electrons that are moving in a given current, times the number of free electrons per unit volume times the drift velocity. And that drift velocity was also a vector. Okay, that's what we found. I I want to say it's in chapter 23. It might be chapter 24, but that's what we found. Okay. So what's going to happen with this setup is we're going to get another electric field established, and that electric field is going to compel, for instance, the electric charges E to move in the direction of E sub H, and that's going to be the force due to the Hall field. Well, guess what? The magnetic field is also going to act on those same charges, and that's going to give you a magnitude of E times the drift velocity times B, because really, remember, it's QV cross B is what the force is. But in this case, the QV is perpendicular to B. So I'll say, so when QV is perpendicular to B, if we look up here at this form right here, we see that we would just get Q times V times B times the sine of 90, and the sine of 90 is 1. Okay, so that's what's going to happen. And in fact, it's going to eventually reach equilibrium so that no more charges are going to be moving. And in other words, it'll set up a little electric field that your voltmeter can detect. And that little electric field is going to cause a difference in voltage that makes the top side of the wire slightly higher voltage than the bottom side of the wire. And that's going to be in equilibrium once this equation right here holds. Okay, that's just from basically E times HF points down and E times VD times B points up. The sum of those two add to give you 0 when there's no more acceleration. So we have that. Now, remember how I told you this looks like a capacitor, and in fact, it behaves like a capacitor because it turns out that the electric potential, which we call it E sub H is actually going to be equal to the Hall electric field times the diameter of the wire. Ooh, let me take a moment and rewrite diameter. Okay. So with that in mind, we can ultimately write that the electric field, or excuse me, the electric potential, oops, change colors and hit the eraser by mistake. The Hall electric potential is going to equal the drift velocity times the magnetic field times D. In other words, all I did was marked out this guy and multiplied both sides by D, and that gave me this equation. Does that make sense?
Why does it have the epsilon symbol?
Because it's not an electric field. This is a voltage, or what we call an electromotive force.
Okay.
And that was one of the symbols we used rather than voltage. Obviously, a V would be a pain here because we got V for velocity. So if you take the time, you can say, I want you to look at example 27-13. It's an easy example, but it basically applies this. And from it, you're able to calculate the drift velocity, because obviously drift velocity, according to this equation, will be the electric potential you measure across the wire divided by the magnetic field times the diameter. and it gets a figure of 4.7 times 10 to the negative fifth meters per second, which is a drift velocity. And then since the drift velocity is given by J equals, this is magnitude now, ENVD, which is also equal to I times area, that means that you can say N, the number of charge carriers per unit volume, is actually the current divided by the electron charge and magnitude times the drift velocity we just found times the cross-sectional area. And lo and behold, when you do this for copper, you get 1111, in other words, times 10 to the 28th. And that's electrons per cubic meter. Which lo and behold is exactly the theoretical value that we calculated when I showed you how to do that in chapter 23 or 24. You basically have now used the Hall effect. Once you read over example 2713, you've now used the Hall effect to confirm what we thought, which was that basically copper gives up a little bit more than 1 electron per atom in being a conductor. So any questions on that? This is all called the Hall effect, by the way. And I hate saying Hall effect because I've always hated the word effects once I learned that how close you can use the two different versions, affect and effect. So anyways, that's the Hall effect. All right, any questions on that?
What's the units for N?
Oh, N is electrons per cubic meter. In this particular case, I just took the time to write that. Your book is just using meters to the -3 power, but I tried to write it as electrons per cubic meter.
Okay.
Okay. So that's one of the things that we can use, this neat aspect of how magnetic fields and electric fields interact, but there's others too. For instance, one of the things, this a little bit goes into, for instance, the Manhattan Project, which I highly recommend reading American Prometheus if you ever get the chance to read anything again other than your textbooks for your classes. But American Prometheus, which is by about J. Robert Oppenheimer. It's by Robert, I think it's by Bird is his last name, K-A-I or something like that. Anyways, it's a great book, one of many great books on the Manhattan Project and Oppenheimer. But anyways, one of the big things that happened when we were trying to create a nuclear weapon, specifically under the concern that, in fact, the Germans were leading the nation, or not the nation, but leading the world in research into what ultimately became nuclear physics. They had people like Heisenberg and Born and a couple other people that were pretty big, and they had done some big things in delving into the nucleus of the atom. And in fact, when Einstein published his special theory of relativity, we discovered that E equals mc squared. And what we learned is that you can take and break apart a big nucleus like uranium-235, say. You can break that apart and out will pop 2 protons and 2 neutrons bonded together, because that's a really, really strong structure called an alpha particle. And that has a mass. And then what you have left is basically uranium-235, but instead of uranium, you have to subtract 2 protons. And then instead of 235, you have to subtract 2 protons and 2 neutrons, because 235 is the number of protons plus neutrons, and you get the new element that comes out of it. Well, if you take the mass of that nucleus plus the mass of the alpha particle, you'll find out that that total mass is less than the mass of the uranium-235. That means the extra mass can be multiplied by c squared to tell you how much energy is given off as a result of that destruction of mass, of that disappearance of mass. And in fact, if you set it up properly, meaning you compel uranium, say 235, or uranium 238 is the better one actually. But if you compel, say, uranium 238 to not only give up a alpha particle, but give up such an alpha particle in such a way that it maybe even can give off another particle that causes the alpha particle to pop loose, then that will cause a second uranium to decay. And because that one did, that will cause another one to decay, and you'll get a chain reaction. And that's what people understood was going to be a huge, huge weapon. So a guy by the name of Leo Szilard, a couple other guys, and Einstein got together, wrote letters. Einstein was quite famous, had just become an American citizen, drove to Washington, D.C., got to meet with the president, gave them a letter saying there's a high probability that one, a big, awful, terrible weapon that literally will be millions of times stronger than any weapon we've ever seen, that anybody's ever seen, but that Germany was in the position to best create such a weapon unless we do it ourselves. So we went about doing that. And one of the big things, at least with the initial bomb, so we tested a bomb over Trinity. They call that the Trinity bomb. That was in Los Alamos, New Mexico. And we tested, I think we tested one more. And then we had to drop one, I say had, but most people agree that we at least shortened the war, if not ended it by doing this. And it's horrible. I'm not trying to make light of this. I mean, literally hundreds of thousands of people died and hundreds of thousands of people got really bad off sick from it, stuff like that. But from a scientific standpoint, what we discovered was that there's very specific isotopes. For instance, hydrogen is hydrogen and it has one proton, but hydrogen's also hydrogen if it has one proton and one neutron, even though we call that deuterium. And hydrogen is also hydrogen, even if it has one proton and two neutrons. And in fact, we call that tritium. And in fact, if you gave it to a chemist, I mean, a smart chemist could actually do the work and figure out that it's not exactly hydrogen. But from a chemistry standpoint, tritium and deuterium behave just like hydrogen. So you could make water out of it, and you can make water out of deuterium, and you can make water out of tritium. And that's, in fact, two different flavors of what we call heavy water. So those three versions of hydrogen are called isotopes. And that's what I mean by that. Well, it turned out when they were studying these nuclear weapons, it turned out that the best things to do, and I'm talking, they went through everything. They went through so much stuff. At one point, they even got basically on the order of 20, 30 kilograms of gold, a solid 20, 30 kilogram chunk of gold to test to see if that would be a better object to use for a nuclear weapon. And then as a joke, they just cut that sphere in half and used it as a door prop. So they literally had a multi-million-dollar door prop that they used at I think that one was at, I think that one might have been in Oak Ridge, Tennessee, but it could have been in Los Alamos. I can't remember. But anyways, they literally had a multi-million-dollar doorstop made out of gold just for the heck of it. But anyways, that particular set of isotopes didn't work out. Uranium-235 worked out really well. Well, actually, uranium-238 worked out really well. Uranium-235 is the one that comes in plentiful amounts. And in fact, you need on the order of, a million or even a billion uranium atoms before you get one uranium-238 atom, and separating them is a big thing. And one of the ways you can separate them is the fact that their nucleus has a slightly larger weight. Now, you can tell it's slightly larger because we're talking 235 versus 238. So we're talking 3 additional neutrons compared to 235 protons plus neutrons, which are about the same weight as each other. So how do you actually do that? How do you select things? Well, one thing you can do is you can accelerate an object, and if it has a certain mass, and you apply a certain force to it, then you know what its acceleration will be. If you let that acceleration go for just say 0.3 of a second consistently, then for a given mass, it will have a given velocity. But if you went to a larger mass, it'll have a smaller velocity. So in principle, you could create a object made to accelerate the nucleus of an atom for a very specific amount of time. And if that particular nucleus of an atom weighed the right amount, then it would have a very specific speed. And then you could use a velocity selector to get rid of all the other possible speeds. So that's what I'm talking about now. And let's do that. So we're going to actually attempt to do a velocity selector. So what we do is we can imagine a slit basically. And basically it'll be two slits. And those two slits, which are really far apart. So you can
Can't
sort of
see it,
imagine, yes, you want to show you my screen, I guess. Thank you. Maybe, come on. All right. So as you can imagine, it's sort of like trying to shoot a BB through a straw. And let's say a really, really long straw. Okay. So that's what you want to do. So let's say you have a particle that wants to go through here. Okay. And what you do is you set up a very specific setup. You're going to make a uniform electric field by making a parallel plate capacitor. And that parallel plate capacitor is going to have positive charges up here and negative charges down here. That's going to create an electric field that tends to make this positive charge, say, go down. Okay. So in fact, F down is going to be equal to the charge Q times the electric field. Now we know for a capacitor, the electric field technically would be sigma over epsilon naught, but that part's not relevant to us. All we care about is an electric field. Okay. So we're just going to say Q times the electric field because the electric field is pointing down. Now, what we can also do though, is we can create a magnetic field, which I shall draw in green again. And this magnetic field is going to point into the page like such, and it's going to be, in fact, uniform. And by being uniform, that means it's going to behave properly so that we know that there will be an upward force. Y'all can use your right hand rule for this one. So the force up in this case is going to be QVB. Again, we're making use of the fact that V is exactly perpendicular to B. Okay. So if you have exactly the right velocity for a very specific velocity, you can choose E and B such that F down or F up, I don't know why it keeps changing that. I do it. It's going to moron mode. F up is equal to F down. So in fact, since it's coming the right direction to begin with, it'll actually make it through both slits. Well, if you do that, what you end up getting is Q times E is equal to Q times V times B, so that V is actually equal to E over B, and you have a velocity selector. So that's one way you could, in principle, separate isotopes. Again, you got to make sure you have the precision to do it, and you may or may not, but that's one of the cases. All right. So that's the other part. That was the last thing I want to talk to you about in chapter 27. Now I need to do one more thing, and we have exactly 10 minutes. So that's about how much time we need. What I'm going to introduce you to is the law of Biot-Savart. So Biot-Savart law. Basically, if you imagine that there's some point over here, P, at which you wish to know B equals question mark, okay, and there happens to be a current carrying wire going by like this, carrying a current I, then you might actually have a little section of wire right here, call it DL, and you might actually draw a vector from here to here, and you might even have a coordinate system set up such that we have a vector. Let's say I'll take a black vector this time. This vector is R sub P because it points to the P. This vector is R sub DL because it points to the DL. And I think you can see from that this vector right here is RP minus RDL. Okay. When you do that, then it turns out that dB, the little bit of magnetic field that you get over there at point B, is given by mu 0 I over 4 pi times DL cross RP minus RDL, all that divided by the magnitude of RP minus RDL. Now it would normally be squared, but because I multiply the top by that vector, I have to multiply it by R in the bottom as well. So I'm going to make it R cubed, and that's the law of Biot-Savart. Okay, let me show you how that's done. It's not nearly as bad as it seems. So let me start by doing this. This will be my z-axis. Okay, what I'm going to imagine is that I have an x-axis pointing this way. And that I have a y-axis pointing into the page. Okay. I'm going to go over here. Now, this by symmetry, I think you can tell something here, but if you can't, don't worry about it. We'll get you there. But this distance right here is going to be a distance r away, even though it's along the z-axis, along the x-axis. And what I'm going to have is a current carrying wire that's infinitely long and parallel to the z-axis, like such. And in fact, it's carrying a current I upward. Okay. And like I said, it goes on forever that way and forever that way. Now, by symmetry of this, I could rotate this iPad all around, and everywhere I go, you could say that's an x-axis. In which case, what you're realizing here is that the actual magnetic field that we're going to get, dB, if you actually work out the cross product and stuff, is actually pointing in the j hat direction. And since it always points perpendicular to that x-axis, it's actually pointing in the theta hat direction. Here we can see it in the j hat direction, but by allowing this whole coordinate system to change by rotating about the z-axis, you can see that that's in fact the same thing as the theta hat direction. So I normally would ask y'all leading questions to try to get you to do all this stuff, but we're running short on time. So what I'm going to do is I'm going to say RP. First off, I'm going to decide what DL is. So what I'm going to say is this right here is DL. Notice it has a very specific length. And in fact, it's a vector that is running parallel to the current. That's important. The DL has to run parallel to the current. It was supposed to do that over here as well. Okay. And it happens to be up a distance Z from the origin. So someone might be able to guess and tell me what DL is going to be. If you know, please shout it out. Otherwise, I'm going to go ahead and write it. Obviously, it's a variation of change of the length Z. So I'm going to call its length DZ. And it obviously points upward, which is the K hat direction. So we're using basically cylindrical coordinates. That also allows me to find a vector that points to it, and that vector is called RDL. So the vector RDL, you guys should try to figure this out on your own before I write it down, but I think you all can tell that RDL should in fact be Z K hat. And then RP, hopefully I think y'all can figure that out as well. RP points from the origin to the point P that we wish to know the electric field at, which in this case is right there. So this is RP. So I'm going to say RP is in fact equal to R, and that points in the I hat direction. So the last part I need for my formula is RP minus RDL and then its magnitude. So RP minus RDL, y'all should be able to work this out on your own right now, even before I do. You should get that that's R I hat minus ZK hat. And you should be able to figure out that the magnitude of that vector RP minus RP minus RDL, which by the way is this vector right here.
Is it the square root of R squared plus Z squared?
Exactly. Good job. Well, yeah, exactly. I thought you said minus for a second there. That's exactly right. So that's going to be equal to the square root of R squared plus Z squared. Good job. So all I have to do is say B is equal to the integral of dB. I don't know why I switched to green all of a sudden, but here we are. That's going to be mu 0 I over 4 pi times the integral of, we now have DL, which is DZ K hat. That has to be crossed with R I hat minus Z K hat. And then all that has to be divided by R squared plus Z squared to the 3/2 power. Now, we're going to make use of the fact that the cross product is a linear operator, and that means I can pull all the stuff out in front. So seeing dz hat cross r I hat minus z k hat looks horrible, and crap, we ran out of time. I'm going to finish this up. If you guys don't have anything urgent, please stay. If you have something urgent, then don't bother. I'm going to go ahead and finish this up. But you all are free to go, and I appreciate you coming. I'm sorry I ran over, but I definitely got to finish this. So I'm going to take the time and do this one bit by bit. So for starters, I can go ahead and call this equal to, and I'm gonna keep blue so we won't get confused as to what we're doing. I can call this dz hat crossed with r I hat, and then I can say plus dz hat crossed with negative z hat. And then I can say this is equal to r dz k hat cross I hat. And I can say minus z dz times, and here's where I'll write this part, it's k hat cross k hat. Anybody know what k hat cross k hat is? It might help to look at this formula. The red.
What was the question?
What is k hat cross k hat?
Would it be 0?
Yep. So that whole term goes to 0, which we sort of expected. We really don't expect to have any terms that would ultimately, be perpendicular to the one that we're going to get, which is ultimately k hat cross I hat gives me j hat. So I'll ask everybody else the other question. What is k hat cross I hat?
One.
Yes, it's 1 times 1 times the sine of 90, which is 1. Now, can you give me the direction using a right-hand rule?
J hat.
Yep, the j hat, which I told you we'll later call theta hat, but j hat's perfectly fine for right now. Good job. So now we got left, going back to my green, is mu 0 I over 4 pi times the integral of r dz over r squared plus z squared to the 3/2. And all of that is times j hat, which I warned you is going to ultimately just become theta hat. Now, to do this integral, oddly enough, it's the exact same substitution we did when we did that Coulombs law. So I'm going to say let z equal to r tangent theta, then dz, then dz would equal r secant squared theta d theta. Okay. So when I do that, I'm going to get mu 0. I'm going to go ahead and pull out some stuff that I knew didn't matter. So for instance, the r that comes out in front, and now I've got the 4 pi down here. And now I'm going to say it's the integral. I'll go ahead and put the j hat out here too. It's the integral of dz becomes r. We've already put one r over there. So I now got another r secant squared theta d theta. And then down at the bottom, I have a common factor of r squared in each term. So I'm going to factor that out. And then I got 1 plus tangent squared theta like that. And all that to the 3/2 power. I think you can now see that the r squared to the 3/2 down on the bottom is going to become r cubed. And on top, we have r squared. So I'm left with mu 0 I over 4 pi r. That's all that's left. And I get the integral of secant squared is on the top. This right here is secant squared, but secant squared to the 3/2 power is secant cubed. So I end up getting secant squared over secant cubed, which means secant in the bottom, but secant in the bottom is the same thing as cosine on top. So I end up getting, oh, I should write that in green. I end up getting the integral of cosine theta, and I'm going to integrate it from negative pi over 2 to pi over 2 d theta. And of course, all that times j hat. And ultimately what you get is b is equal to, now the derivative of sine is cosine, so the integral of cosine sine. So I'm just going to get sine. The sine of pi over 2 is just 1. And then minus the sine of negative pi over 2, which is -1. So minus negative would be 2. So I'm just going to get mu 0 I over 2 pi r instead of 4. So 2 pi r. And as I told you, from a symmetry standpoint, we can go ahead and call that the theta hat direction instead of the j hat direction. And that happens to be exactly the right answer. And I ran over by 8 minutes. Any questions on that? That's a fairly non-trivial problem, I guess, is a slight understatement, maybe. But that's not a lot different, for instance, from what we did on Coulombs Law on day 1 or day 2, when I actually used that vector form of Coulombs Law. So this form that I wrote up there of the law of Biot-Savart, that's a hyphen, by the way, between them. That law is written in a way that your book doesn't write it, and you are welcome to use that version on your equation sheet, both on your obviously on your online test, but also on your final as well. Really should have been blue. So anyways, this one right here.
Okay.
Oh, that Z is not supposed to be in there. Let me fix all this a little bit. And let me fix that too. That looks ugly. And now let me circle this in a real color. So this is the law of Biot-Savart in a differential vector form. So it's actually, though it looks a lot more complicated, because in some sense it is, but it's very prescriptive. You've got exactly a set of steps that you need to fulfill. You've got to identify DL, right? That happens to be a little line segment of infinitesimal length, DL, in our case it was DZ, that points, because it's a vector, points the same direction as the current I, and it has to be along the wire carrying the current. That's all you got to do with the DL. The RP has to be a vector from whatever origin you choose to the point P at which you wish to know the magnetic field. The vector RDL has to point from that same origin that you chose to that differential line element vector DL. So you just got to find those three things. Once you found those three things, you've got to compute RP minus RDL. Then you've got to compute the magnitude of RP minus RDL using the Pythagorean theorem. Okay. Then you put all that in there. And once you've done that, you've got the physics done. The rest is not physics. The rest is mathematics. This is why I tell people, you know, on a midterm and a final, sometimes I'll have a question or a series of questions or two questions where I'll say, okay, during this test, I want you to, during this particular problem, I want you to write as neatly as you can your solution to this problem. And you have 15 minutes after submitting your exam to take a photograph of your work and email it to me. And when I say that, I mean for that particular problem, not all your work, just the work for that problem. So for instance, if you did all that and you got to, let's say, you got to this stage right here, then in my estimation, you should probably get at least 95, 98% of the points. Because at that point, you've done the physics, right? The physics is what matters. I'm teaching a physics class, not a math class. So keep that in mind. Hopefully people will watch this video that left early, that sort of thing. I'm slowly trying to cut out the beginnings of these videos where I waste, you know, several minutes. And I say waste, but it's good stuff. I'm talking to you guys, but it's just not stuff that, you know, rando wants to read. So I'll be trying to cut that out. But anyone have any questions? Anyone need me to flip back to some other page or anything like that?
No.
Okay. Pay attention to your email. I may or may not be putting up 2 more practice tests and actual tests. And when I do that, those tests will be super helpful in you working towards your preparing for the midterm. And not only that, the chapter assignments that I put up that don't count for any grades, you know, like you have chapter 27 questions, chapter 26 questions. Those are going to be up till May 9th. And y'all, I mean, if you find you're running kind of weak in chapter 27, then do a bunch of those questions. I don't, you know, I'm not giving you any credit for them or anything, but at the same time, you're not losing any points and you're getting a lot of experience. So if you feel like, oh crap, I wish I would have done practice test 2 a little bit more, all you have to do is chapter 3 or chapter 4 questions over and over again, and you'll get plenty of experience. So everybody's free to go, of course, again. So I'm going to go ahead and stop sharing, but wait. And if anybody has any questions, I'm here to answer them. And once the last person leaves, I will split as well.
I'm sorry, I have one question. I accidentally missed when you were saying when is the date of the midterm again? Or when is
Okay,
midterm
so
gonna be?
it'll be the Thursday when we get back from spring break. Spring break is from March 5th to March 12th. So it'll be the 16th.
16th. All right, thank you, sir.
And
You have a
you're
good night.
supposed to email me if you can't start at least 20 minutes early or you can't finish at least 20 minutes late. Okay, so make sure you know you do that.
Okay, so that means that you're starting like 20 minutes before, or like at class.
Yeah, I'm trying to give you a full 2 hours instead of just an hour, or excuse me, instead of an hour and 20, I'm trying to give you an hour and 40, maybe even 2 whole hours. I'll send some details about that. I just realized your class starts at 5:20, so it's only an hour and 20 that you normally get. But I'm trying to give you as much time as possible, but all I have to have is one student that can't come early or stay late, and then I can't offer it for anybody. So ideally, I'd like to do a full 2 hour midterm.
All right. Thank you very much. Yeah, I'm still trying to study. I haven't really much time to study, so I'm trying to study. I'm just making sure I'm studying.
No problem.
For midterm. So
Make sure you
have a good night,
contact me
sir.
if you have any questions. If you have a problem, like on one of the practice tests, take a screenshot of it with the multiple choice answers and send it to me via text or email. Text is a little bit more reliable. I answer my emails. It's just sometimes that I miss them because people don't put the subject line in right, and then other times I just don't get them. And sometimes I just evidently don't look at them because I don't know, I'm a moron, I guess. But so feel free to text me Any kinds of questions you have, I'll set up on weekends or any time like that. I'll set up Zoom meetings privately or whatever. So let me know if I can help anybody.
All right. Thanks.
You're welcome. Maya, Famata, John, Joseph, Jingleheimer Schmidt. It just had a nice ring to it. Anybody have any questions? John Jacob Jingleheimer Schmidt. His name is my name too. I'm probably gonna find out that.
Professor Young.
Yes, ma'am. Go for it, Famata.
Yeah, I have a question.
Oh, is it Maya? Sorry. Go for
No,
it.
you're fine. So back on the page where you had the Hall effect,
Uh-huh.
when you were doing the right-hand rule, when it was the positive current pointing to the left, can you explain that
Yes.
again? Positive.
Yeah.
still trying-
Okay. So I'm trying to share the screen with you right quick now. So with the positive charge, whoop, that's not the right one. That was velocity selector. There it is. Okay. With the Hall effect. So with the positive charge, any scalar times a vector just gives you a longer or shorter vector. If the number is bigger than 1, it's going to give you a longer vector. If the number is smaller than 1, it's going to give you a shorter vector, as long as the scalar is positive. But if the scalar is negative, it's also going to flip its direction 180 degrees. In this case, you're
Okay.
asking about the positive charge though, right?
Yes.
Okay, so QV is actually the same direction as V. And since the current's going to the left, that means the V is going to the left for the positive particles.
Okay, so since it's positive, it goes
Exactly.
the same direction. Basically, is what you're saying.
Right. So you stick your index
So-
finger to the left. Go ahead. You can go.
Oh, so since it was QV and since that was the positive charge, that's why it stays going in the same direction. But if it was negative, it would flip it.
Exactly.
Okay.
So you figured it out already.
And then with the right hand rule, yeah. So with the right hand rule, so I mean, I know it's inverted for me and you, but I do have my thumb up and then I flip my finger so my middle finger points into it would be pointing away from me, right? For that one.
Yeah, into the screen or into the paper or whatever. Yes.
Okay. And then it's still pointing the left to the left.
Yep.
Okay. And then for the negative. So yeah, how does it work with the right hand rule? How does it work when it's pointing to the right? Since we
Okay. So in this case, it's electrons which are negatively charged and they're moving to the right. But when you multiply a negative number times a velocity to the right, you get a velocity to the left. So you're literally doing the exact same thing as you did with the positive ones.
Oh, okay. Oh, I see.
So you move like that and you see it points down again.
Yeah.
Isn't that cool?
Okay. Yeah, that's pretty helpful. Yes.
No problem. Anybody else? I appreciate you asking questions. I worry about how few people do ask questions. So by all means, I'm loving that you're asking them. So keep it up.
Thank you. Just for the midterm, so it's on chapters 21 through what would it be, 28?
That's what I'm leaning towards right now, 21 through 28. 21, 22, 23, 24, 25, 26, 27, 23. It actually might be 21 through 27 or even 26.
Okay.
I'll let y'all know ahead of time, but yeah, it might not be long enough to go through 28.
Okay.
Okay.
Thank you so much.
You're welcome. Bye.
Bye.
Anybody else?
Yes, so I sent you an email and I realized that I did not